Hey everyone, today I'm going to be giving a lesson on Cherenkov radiation, a concept which I encountered studying for the GRE last night. And yeah, let's get right into it. So Cherenkov radiation, spelled I think this way, but I probably got that wrong, is basically a result of the fact that there's a thing called an index of refraction. And an index of refraction is a ratio between the speed of light in vacuum, or the speed of causality, or whatever you want to call it, and the speed of light in a medium. So what this concept is saying is that the speed of light is not the same in all mediums, right? And so some people say, a lot of people say, can't go faster than the speed of light, otherwise you go back in time. Which is true if you are talking about the speed of light in vacuum, which is c, which is, I'll do a squiggly, roughly 3 times 10 to the 8 meters per second. Everybody knows that number, everybody loves that number. Okay? That's as fast as you can go in the universe, infinity, a million years ever. You can't go any faster than that. However, if you are in, say, like water, which has an index of refraction of about 1.33, the speed of light is no longer that. Okay? It's now that divided by n, because v, which is the speed of light in a medium, is equal to, if I just change it around, c divided by n. So I can go faster than that. I can go faster than this divided by that. And what that's saying is, if I have a particle that is traveling with a speed, vp, so, velocity or speed of my particle, and that is greater than v, well, we'll say c over n of my material, and we're going to say water, and you'll see why. That's greater than c over n water, or you can think of this as what's called the phase velocity of light in my material, or my medium. Phase velocity of light in water. Phase velocity of light in water. Okay? If I'm going faster than the phase velocity of light in water, but I'm still going slower than c, I'm sorry, these are backwards. Oh my gosh. These are backwards. Alligator eats the bigger fish, okay? Vp is greater than phase velocity of light in water, but Vp is still less than c, less than 3 times 10 to the 8 meters per second. This is fine. Physics says you can totally do that. You can go this speed. There's like a little pocket in there where you're going faster than this thing, but slower than that thing. That's a-okay. And that's actually, it's not a big coincidence that you end up in that pocket, because you can't ever reach that. So it's pretty easy to end up there. As long as you go faster than this, you pretty much have to be in that pocket. Anyway, so what does that mean? So what happens? Okay, well, let's say, for example, I have an electron, and the reason I'm using an electron is because of a thing called Bremsstrahlung radiation, which we all know, right? That's the radiation emitted from a charged particle under acceleration. So if I speed up or slow down a particle with charge, an electron or proton or whatever, it emits light. That's it, okay? If I have an electron, it's got a little minus in it, so make the minus a little bigger, traveling with this Vp, and it's being accelerated due to the fact that it's traveling in matter, in water. It's just slowing down because that's what happens when you travel in matter. It can't emit. It's saying, I'm going to shoot photons in a sphere in every direction, okay? Here they go. I'm shooting photons. That's a weird arrow. I'm shooting photons, but the photons I shoot forward can't go any faster than me. It works just like a shock wave in air. They can't propagate forward. The waves cannot propagate forward any faster than this thing can also propagate forward. So that one goes away, and kind of that one goes too. The end effect is just exactly like a shock wave in air. You get a shock front of propagated light, just like this. It's just like light shock waves. So if your physics professor ever asks you, hey, smarty, what's Cherenkov radiation? You just say, it's shock waves of light. And he'll be like, whoa, you're so cool. You're probably the coolest person I ever met. He's definitely going to say that. So just keep that in the back of your mind. Anyway, these propagate out. So if you want to see Cherenkov radiation, all you have to do is look up a fission reactor that's water cooled specifically. What you'll see is, and you might even have a picture of this in the back of your head somewhere, a fission reactor in the movies or in just a real picture of one, they're always glowing blue. They're always like glowing blue if they're underwater. It's really strange. The reason why is because fission reactions create a lot of electrons that travel at very high speeds, VPs. So they travel faster than the speed of light in water, and when they hit that water, they shoot these fronts off because the light can't propagate forward in Cherenkov radiation. So why is it blue? Well, that comes down to a formula called the something blah blah formula. It's the something tam formula. The Frank-Tam formula. Frank-Tam formula. And basically what that formula says in math is that it's not a characteristic specific wavelength of light that is emitted on these shocks or these fronts. It's a continuum of light based on the acceleration of the charged particle. So if it's accelerating more, then you get a different wavelength than if it's accelerating less. And in the case of our universe, if it's accelerating more, the wavelengths tend to be larger. So it starts off in like, super tiny wavelengths, very high energy, photons come off. But the more you accelerate the light, the less, the bigger those wavelengths get, and they go into the optical range. And so the level below UV, or the smallest wavelength, is like blue, like violet and blue. So you get a nice, beautiful, deep blue color coming from all your fission reactors, and you don't even have to pay for LEDs. That's the end result. Thanks for watching.